In this very moment, as you listen to these words, 37 trillion cells are quietly coordinating one of nature's most elegant transitions. Your heart rate is beginning to slow from its daytime urgency, dropping perhaps 10 to 20 beats per minute. As evening settles around you, your core body temperature is starting its gradual descent, a signal as ancient as sleep itself that tells every organ system to shift into its nocturnal rhythm. This is not simply relaxation, this is biological architecture in motion, a masterpiece of human anatomy, preparing itself for the profound restoration of sleep. Within your skull, neurons are already adjusting their electrical conversations, dimming the bright chatter of consciousness, while awakening the deeper networks that govern dreams and memory consolidation. Your muscles are releasing the subtle tensions they have carried throughout the day, each fiber group surrendering to gravity's gentle pull. Even your bones, those seemingly inert pillars of calcium and phosphate, are stirring with their own quiet activity, as specialized cells begin the overnight work of repair and renewal. Tonight, we embark on a different kind of journey through the human form, not the urgent examination of medical textbooks, but a gentle exploration of the living systems that sustain you. We will discover how your skeleton provides not just structure, but sanctuary, how your cardiovascular network becomes a river of restoration, and how your nervous system orchestrates the profound mystery of sleep itself. Each system we explore is working within you at this very moment, maintaining the delicate balance that allows consciousness to fade and dreams to flourish. Let your breathing deepen as we begin this anatomical lullaby, a celebration of the remarkable biological symphony that grants you the gift of peaceful rest. I'm curious to know where you're listening from tonight, and what time it is in your part of the world. It brings me such joy to know that wherever you are, we're sharing this quiet moment of discovery together. Let's get into the video. Beneath your skin and muscle lies a framework more enduring than any cathedral, more intricate than any architectural marvel humans have ever conceived. Your skeleton is not merely a collection of rigid supports, but a living ecosystem of calcium, phosphate, and protein that rebuilds itself continuously throughout your lifetime. As you rest here now, this bony architecture is engaged in its own quiet choreography of maintenance and renewal, a process so gradual and gentle that it never disturbs your peaceful transition into sleep. Consider the remarkable substance that forms your bones, calcium phosphate crystals, arranged in microscopic patterns more precise than any engineer's blueprint, provide strength that rivals concrete while maintaining a lightness that allows you to move with grace. These crystals are embedded within a matrix of collagen, that flexible protein that gives bone its ability to bend rather than shatter under stress. Together, they create a composite material that is both harder than steel and more flexible than wood, a biological masterpiece that has evolved over millions of years to support and protect the soft treasures within. Your bones are not the static, museum-piece structures that many imagine. They are dynamic, living tissues coursing with blood vessels and populated by specialized cells that work in perfect harmony. Osteoblasts, the builders, secrete new bone material in response to the stresses and demands of daily life. Osteocytes, the maintenance crew, monitor the health of existing bone and coordinate repair efforts. And osteoclasts, the renovators, carefully dissolve old or damaged bone tissue, making way for fresh construction. This cellular ballet occurs continuously, replacing your entire skeleton approximately every 10 years, while you remain blissfully unaware of the transformation. During these quiet evening hours, as your body settles into rest, your bones undergo their most intensive period of remodeling. The mechanical stresses of walking, lifting, and moving throughout the day have sent signals throughout your skeletal system, informing each bone where strengthening is needed and where resources might be redistributed. Now, in the stillness of approaching sleep, your bone cells respond to these messages, laying down new mineral deposits in areas that bear the most load and carefully recycling calcium from regions where it is less needed. The joints where your bones meet are marvels of biological engineering that would humble any human inventor. Synovial joints, those that allow free movement like your shoulders and knees, are enclosed in tough capsules filled with a remarkable lubricant called synovial fluid. This golden, honey-like substance has a viscosity that changes with movement, becoming thinner when your joints are active to reduce friction, and thicker when you are still to provide cushioning and stability. As you lie here now, this fluid is coating the cartilage surfaces of your joints with a protective film that is 10 times more slippery than ice on ice. The cartilage itself is a wonder of biological architecture, composed primarily of water held within a framework of specialized proteins. It provides a smooth, resilient surface that can withstand pressures equivalent to several times your body weight without showing wear. Unlike other tissues, cartilage has no blood supply of its own. Instead, it receives nutrients through the gentle pumping action that occurs when you move, squeezing waste products out and drawing fresh nutrients in like a biological sponge. During rest, this cartilage swells slightly as it absorbs fluid, preparing for tomorrow's activities while contributing to that gentle settling sensation you might notice as your joints release the day's tensions. Hidden within the hollow spaces of your larger bones lies one of your body's most vital factories, the bone marrow. This soft, gel-like tissue exists in two forms, each with its own essential function. Red bone marrow, found primarily in your ribs, spine, pelvis, and the ends of long bones, is responsible for hematopoiesis, the continuous production of blood cells. Even as you rest, this marrow is generating approximately 200 billion red blood cells, 10 billion white blood cells, and 400 billion platelets each day. The process of blood cell formation is a testament to the body's remarkable efficiency. Stem cells within the marrow divide and differentiate into the various types of blood cells your body needs, responding to chemical signals that indicate demand. If you have been fighting an infection, more white blood cells will be produced. If you live at high altitude, additional red blood cells will be manufactured to carry more oxygen. This production continues around the clock, but it peaks during the quiet hours of sleep, when your body can dedicate more resources to this essential manufacturing process. Yellow bone marrow, composed primarily of fat cells, serves as both an energy reserve and a backup blood-producing facility. During times of severe blood loss or illness, this yellow marrow can transform back into red marrow, dramatically increasing your body's capacity to produce new blood cells. This remarkable adaptability ensures that your skeletal system is not merely a structural support, but an active participant in maintaining your health and vitality. As sleep approaches, your bones undergo subtle but important changes in their mineral content. The slight decrease in mechanical loading allows for a redistribution of calcium and phosphate, with these minerals moving from areas of high stress to regions where they can be stored for future use. This process is orchestrated by hormones that follow their own circadian rhythms, ensuring that bone remodeling occurs at the optimal time for healing and strengthening. The mineral composition of your bones tells a story of constant adaptation written in calcium and phosphate. These minerals do not simply accumulate randomly, but are deposited according to the precise mathematical principles that govern crystalline structures. Hydroxyapatite crystals, the primary mineral component of bone, align themselves along the lines of mechanical stress, creating internal architecture that rivals the flying buttresses of Gothic cathedrals. This alignment is not accidental, but represents millions of years of evolutionary refinement, producing a material that can withstand tremendous forces while remaining light enough for efficient movement. The process of bone mineralization follows a circadian rhythm that peaks during the hours of rest. As you lie here now, specialized transport proteins are moving calcium ions from your bloodstream into your bones, while other proteins carefully regulate the pH levels necessary for proper crystal formation. This delicate chemical ballet requires precise coordination between your endocrine system and your skeletal cells, with hormones like parathyroid hormone and calcitonin fine-tuning the process moment by moment. Within the microscopic structure of your bones, tiny channels called canalicula create an intricate network that would put any telecommunication system to shame. These hair-lined passages, no wider than a few micrometers, allow bone cells to communicate with each other through chemical signals and electrical impulses. When you apply pressure to a bone by walking or exercising, these channels carry the mechanical signals throughout the bone tissue, informing cells throughout the structure about where strengthening is needed. During rest, this network continues to hum with activity, as cells share information about the day's stresses and coordinate their repair efforts. The collagen fibers that form the organic framework of your bones are arranged in patterns that maximize both strength and flexibility. These protein strands twist together like microscopic ropes, creating a matrix that can stretch and compress without breaking. The relationship between collagen and mineral crystals in bone is so perfectly balanced that removing either component dramatically weakens the structure. Young bones rich in collagen can bend considerably without breaking, while older bones with higher mineral content become harder, but more brittle. Your body continuously adjusts this balance throughout your lifetime, responding to your activity levels and mechanical demands. The periosteum, that fibrous membrane surrounding each bone, serves as both protector and nurturer. This seemingly simple layer contains blood vessels that penetrate deep into the bone tissue, carrying nutrients and removing waste products. The periosteum also houses stem cells that can transform into bone-building osteoblasts when repair is needed. During sleep, blood flow to the periosteum increases, delivering the raw materials necessary for overnight bone maintenance and growth. Your spine, that remarkable column of 33 vertebrae, demonstrates the skeletal system's ability to combine stability with mobility. Each vertebra is separated by an intervertebral disc, a structure that functions as both shock absorber and flexible joint. These discs consist of a tough outer ring surrounding a gel-like core that can compress and expand to accommodate movement. During the day, the constant pressure of gravity compresses these discs slightly, but as you lie down to rest, they gradually rehydrate and expand, actually making you slightly taller by morning. The intricate curves of your spine, the cervical lordosis in your neck, the thoracic kyphosis in your upper back, and the lumbar lordosis in your lower back, work together to distribute the weight of your head and torso efficiently. These curves are not arbitrary, but represent the optimal engineering solution for a creature that walks upright. As you settle into sleep, these curves relax into their natural positions, allowing the muscles that support them to release their constant vigilance. The calcium stored within your bones serves as more than structural material. It functions as a vast mineral bank that your body can draw upon to maintain the precise calcium levels required for muscle contraction, nerve transmission, and blood clotting. Your bones contain 99% of your body's calcium, and they continuously exchange this mineral with your bloodstream to maintain the delicate balance necessary for life. During sleep, when you are not consuming calcium-rich foods, your bones become the primary source of this essential mineral, releasing it in carefully measured amounts to meet your body's ongoing needs. The formation of new bone tissue requires a complex orchestration of growth factors, hormones, and mechanical signals. Growth hormone, released primarily during deep sleep, stimulates the production of insulin-like growth factor, which in turn promotes the activity of bone-building cells. This hormonal cascade ensures that the most intensive bone formation occurs during the hours when your body can dedicate maximum resources to repair and growth. The wisdom embedded in your skeletal system extends beyond its individual components to encompass the entire framework as a unified structure. The curves of your spine, the angles of your joints, and the proportions of your limbs all work together to distribute weight and absorb shock in ways that minimize stress on any single component. As you settle into rest, this framework adjusts itself subtly, allowing the natural curves to settle into their most comfortable positions, and relieving the small tensions that accumulate throughout the day. Your skeleton is more than the sum of its parts. It is a living testament to the elegance of biological design, a structure that combines strength with flexibility, permanence with adaptability, and function with beauty. As you drift towards sleep, take comfort in knowing that this remarkable framework will continue its quiet work of maintenance and renewal, ensuring that, when you wake, you will be supported by bones that are slightly stronger, slightly more perfectly adapted to your needs, and ready to carry you through another day with grace and resilience. In the gentle transition towards slumber, your skeletal foundation settles into its own rhythm of rest and restoration, a biological bedrock that will cradle your dreams and guard your sleep until morning light calls you back to wakefulness. As your skeleton provides the architectural framework for rest, your muscular system orchestrates the gentle choreography of relaxation that guides you towards sleep. 3 distinct types of muscle tissue work in harmony throughout your body, each following its own rhythm as evening settles around you. Some muscles you control consciously, others work tirelessly without your awareness. And one very special muscle beats with a rhythm that has marked every moment of your existence since before your first breath. Deep within your organs, smooth muscle tissue conducts a quiet symphony of involuntary movements that continue even as consciousness fades. These elongated, spindle-shaped cells lack the striations that characterize their skeletal cousins, yet they possess a remarkable ability to maintain sustained contractions with minimal energy expenditure. As you rest here now, smooth muscle in your digestive tract is orchestrating the gentle waves of peristalsis that will process your evening meal throughout the night. These rhythmic contractions move food through your intestines with a patience that mirrors the slow deepening of your breath. The smooth muscle cells in your stomach wall are adjusting their tone, accommodating the contents within while secreting digestive juices in carefully measured amounts. Unlike the rapid, forceful contractions of skeletal muscle, smooth muscle works with a deliberate, almost meditative pace. Each contraction can last several seconds or even minutes, creating sustained pressure that gradually propels materials through your digestive system. This extended duration is possible because smooth muscle cells can maintain their contracted state with remarkably little energy, allowing them to work continuously without fatigue. Your blood vessels are lined with smooth muscle that responds to chemical signals and neural commands with exquisite sensitivity. As your body prepares for sleep, these vascular smooth muscles are making subtle adjustments to blood flow, redirecting circulation away from active tissues and toward organs involved in repair and maintenance. The smooth muscle in your skin's blood vessels is relaxing, allowing heat to radiate away from your core and contributing to the slight drop in body temperature that signals your brain to begin the sleep process. In your respiratory system, smooth muscle in the walls of your bronchioles is adjusting airway diameter with each breath, fine-tuning the flow of air to different regions of your lungs. These muscles respond to carbon dioxide levels in your blood, opening wider when more ventilation is needed, and narrowing slightly as your breathing slows and deepens with approaching sleep. The coordination required for this constant adjustment occurs entirely below the threshold of consciousness, a testament to the sophisticated control systems that govern smooth muscle function. The smooth muscle in your urinary system demonstrates remarkable adaptability as it prepares for the long hours of sleep ahead. The detressor muscle in your bladder wall can stretch to accommodate increasing volumes of urine while maintaining just enough tone to prevent unwanted emptying. Meanwhile, the smooth muscle sphincters that control urinary flow are increasing their vigilance, ensuring that sleep will not be unnecessarily interrupted. This delicate balance between accommodation and control exemplifies the wisdom embedded in smooth muscle function. At the center of your chest, your heart maintains its eternal rhythm with a muscle type found nowhere else in your body. Cardiac muscle combines the strength and precision of skeletal muscle with the tireless endurance of smooth muscle, creating a tissue perfectly adapted for its vital role. Each cardiac muscle cell, or cardiomyocyte, is connected to its neighbors through specialized junctions called intercalated discs, creating a synchronized network that ensures your heart beats as a unified whole. The intrinsic rhythm of your heart originates in a small cluster of specialized cardiac cells in your right atrium called the sinoatrial node. These pacemaker cells generate electrical impulses at a rate that varies with your body's needs, slowing as you transition towards sleep and accelerating when activity demands increase. The electrical signal spreads through your heart muscle like ripples across a pond, causing the chambers to contract in the precise sequence necessary to pump blood efficiently throughout your body. As you rest here now, your heart rate is gradually decreasing from its daytime pace of perhaps 70 to 80 beats per minute to the slower rhythm of approaching sleep, possibly dropping to 60 beats per minute or even lower. This reduction is not simply a matter of decreased demand, but an active process coordinated by your autonomic nervous system. The parasympathetic branch of this system is releasing acetylcholine at nerve endings in your heart, causing the pacemaker cells to slow their firing rate and extending the intervals between heartbeats. The cardiac muscle itself is undergoing subtle changes in its contractile strength as sleep approaches, while maintaining the force necessary to circulate blood effectively. The heart muscle is optimizing its efficiency, extracting maximum work from each contraction while minimizing energy expenditure. This cardiac economy is achieved through precise regulation of calcium flow within the muscle cells, allowing for strong contractions followed by complete relaxation between beats. Your heart's electrical system follows its own circadian rhythm, with subtle changes in conduction velocity and refractory periods that occur throughout the day and night. During sleep, the electrical pathways through your heart become slightly slower and more stable, reducing the likelihood of irregular rhythms and promoting the steady, even heartbeat that characterizes peaceful rest. This electrical stabilization is supported by changes in ion channel activity within the cardiac muscle cells, creating conditions that favor regular, predictable contractions. The skeletal muscles that move your limbs and support your posture are beginning their own transition toward the profound relaxation of sleep. These voluntary muscles, composed of long, multinucleated fibers marked by distinctive striations, have carried you through the day's activities and are now ready to surrender to gravity's gentle pull. Each skeletal muscle fiber contains thousands of myofibrils, those microscopic contractile elements that generate movement through the sliding of actin and myosin filaments. As you settle into rest, the motor neurons that control your skeletal muscles are reducing their firing rate, allowing muscle tension to gradually decrease. This process occurs in waves, starting with the larger muscle groups and progressing to the smaller stabilizing muscles. Your shoulders may be the first to release their grip on the day's tensions, followed by your arms, your back, and finally the intricate muscles of your face and neck. The mechanism of skeletal muscle relaxation involves more than simply stopping the signals that cause contraction. Specialized proteins within the muscle fibers actively promote relaxation by sequestering calcium ions, the key triggers for muscle contraction. As calcium is pumped back into storage compartments within the muscle cells, the contractile proteins lose their ability to interact, and the muscle fibers lengthen under the gentle influence of gravity and passive stretch. Muscle spindles, those sophisticated sensory organs embedded within your skeletal muscles, are adjusting their sensitivity as your body prepares for sleep. These remarkable structures contain modified muscle fibers that can detect changes in muscle length and rate of stretch with extraordinary precision. As you transition towards sleep, the nervous system adjusts the sensitivity of these spindles, reducing their responsiveness to minor position changes and allowing for the deeper relaxation necessary for restorative rest. The energy systems within your skeletal muscles are shifting into their nocturnal mode of operation. During sleep, muscle tissue becomes a major consumer of growth hormone, using this powerful anabolic signal to repair microscopic damage accumulated during daily activities and to build new contractile proteins. The process of protein synthesis within muscle cells peaks during the deep sleep phases, when growth hormone levels are highest, and the muscle fibers can dedicate their resources to maintenance and growth rather than contraction. Blood flow to your skeletal muscles is gradually decreasing as the demand for oxygen and nutrients diminishes with reduced activity. However, this reduction is carefully regulated to ensure that adequate circulation is maintained for the important repair processes that occur during sleep. The capillary networks within your muscles remain open, allowing for the delivery of amino acids, glucose, and other building blocks necessary for overnight tissue maintenance. As your muscular system settles into its pattern of nocturnal rest and repair, each type of muscle tissue contributes to the overall sense of peace and relaxation that characterizes the transition towards sleep. Smooth muscles continue their patient work of digestion and circulation. Cardiac muscle maintains its steady rhythm with quiet efficiency, and skeletal muscles release their hold on the day's tensions, allowing your body to settle into the supportive embrace of whatever surface holds you. This muscular surrender is not a sign of weakness but of wisdom, a biological understanding that rest and repair are as essential as action and movement in the continuous cycle of life. Within the protected fortress of your skull and the flexible column of your spine lies the most sophisticated information processing system known to exist in the universe. Your nervous system is conducting an intricate evening symphony right now, gradually shifting from the bright alert melodies of daytime consciousness to the deeper, more mysterious harmonies that will guide you into sleep. This transition involves billions of neurons adjusting their electrical conversations, neurotransmitters changing their chemical songs, and entire brain regions modulating their activity in preparation for the restorative journey ahead. Your brain, weighing approximately 3 pounds yet consuming 20% of your body's energy, is orchestrating this transition with remarkable precision. The cerebral cortex, that wrinkled outer layer where conscious thought occurs, is beginning to quiet its chattering networks of activity. The frontal lobe, responsible for executive decisions and complex reasoning, is gradually reducing its electrical intensity as the demands for focused attention diminish. Meanwhile, deeper brain structures are awakening to their nocturnal duties, preparing to guide you through the essential phases of sleep that will restore your mind and consolidate the memories of the day. The hypothalamus, a small but mighty structure deep within your brain, serves as the master conductor of this evening symphony, no larger than an almond. This remarkable region contains your body's primary biological clock, the suprachiasmatic nucleus, which has been tracking the passage of light and darkness throughout the day. As evening light fades, this internal timekeeper begins releasing melatonin from the nearby pineal gland. That ancient structure once called the third eye. Melatonin molecules spread through your bloodstream like chemical messengers, informing every cell in your body that night has arrived and rest is approaching. The thalamus, your brain's sensory relay station, is beginning to filter the flood of information from your senses with increasing selectivity. Throughout the day, this structure has been dutifully forwarding sensory signals to your cortex for conscious processing. But now it starts to close certain channels, reducing the intensity of sounds, dimming the perception of light, and allowing touch sensations to fade into the background. This sensory gating is not a simple on-off switch, but a gradual dimming that allows your conscious mind to disengage from the external world, while maintaining enough awareness to respond to truly important stimuli. Your cerebellum, that densely folded structure at the back of your brain responsible for balance and motor coordination, is adjusting its activity as your body settles into stillness. The constant fine-tuning of muscle tension and postural adjustments that mark your waking hours is giving way to a deeper relaxation as your cerebellum reduces its vigilant monitoring of movement and position. This allows your body to settle into sleep positions that might be uncomfortable during waking hours, as the neural systems that normally protest against prolonged static postures become less insistent. The brainstem, containing the medulla pons and midbrain, continues its vital work of maintaining basic life functions while adapting to the requirements of sleep. Your medulla is adjusting the rhythm of your breathing, slowing it from the variable patterns of waking activity to the deeper, more regular respirations of approaching sleep. The pons, which plays a crucial role in REM sleep, is preparing for its starring role in the dream-rich phases that will come later in the night. These ancient brain structures, evolved long before consciousness as we know it, possess an innate wisdom about the rhythms of rest and restoration. Cerebrospinal fluid, that clear, protective liquid that bathes your brain and spinal cord, is beginning to flow with increased vigor as sleep approaches. Recent discoveries have revealed that this fluid circulation increases dramatically during sleep, washing away metabolic waste products that accumulate in brain tissue during waking hours. The glymphatic system, as this cleaning mechanism is called, operates like a neural dishwasher, using the pulsing of cerebral blood vessels to drive cerebrospinal fluid through tiny channels between brain cells, carrying away toxic proteins and cellular debris that could otherwise impair brain function. Your spinal cord, that vital information highway connecting brain to body, is adjusting its transmission properties as sleep approaches. The neural pathways that carry pain signals are becoming less sensitive, allowing minor discomforts that might be noticeable during the day to fade below the threshold of awareness. Meanwhile, the motor pathways that control movement are being gradually inhibited, preparing for the muscle atonia that will prevent you from acting out your dreams during REM sleep phases. The peripheral nervous system, that vast network of nerves extending throughout your body, is shifting from its daytime mode of vigilant sensory monitoring to a more selective nighttime surveillance. Sensory neurons in your skin are reducing their sensitivity to light touch, while maintaining their ability to detect potentially threatening stimuli. The proprioceptors that inform your brain about the position of your limbs are scaling back their constant chatter, allowing for the disorientation of limb position that characterizes the transition into sleep. Your autonomic nervous system, the part that controls involuntary functions, is undergoing perhaps the most significant transition of all. The sympathetic branch, which has maintained your daytime alertness and readiness for action, is gradually yielding control to the parasympathetic branch, often called the rest and digest system. This shift is orchestrated by changes in neurotransmitter release at nerve endings throughout your body. Norepinephrine, the chemical messenger of alertness and arousal, is being scaled back, while acetylcholine increases its influence, promoting relaxation and restoration. The vagus nerve, the longest cranial nerve and a key component of the parasympathetic system, is extending its calming influence throughout your body. This remarkable nerve, which wanders from your brainstem to your abdomen, is slowing your heart rate, stimulating digestion, and promoting the release of anti-inflammatory compounds. The increased vagal tone that accompanies sleep preparation helps explain the sense of calm and well-being that often accompanies the transition toward rest. Sensory systems throughout your body are adapting to the changing requirements of sleep. Your visual system is adjusting to decreased light levels, with pupils dilating slightly and retinal sensitivity increasing. The photoreceptors in your eyes that detect blue light, the primary signal for daytime alertness, are becoming less active, removing one of the strongest wake-promoting stimuli. Your auditory system is maintaining vigilance for important sounds, while filtering out the constant background noise of daily life, creating the selective hearing that allows you to sleep through routine sounds, while remaining responsive to your name or unusual noises. Your sense of smell, so closely connected to memory and emotion, is preparing for its enhanced role in sleep. During certain phases of sleep, olfactory processing increases, and scent memories become more vivid. This heightened olfactory sensitivity during sleep may explain why certain smells can trigger such powerful dream memories, or why aromatherapy can be effective for promoting restful sleep. The intricate dance of neurotransmitters in your brain is shifting toward the chemical symphony of sleep. GABA, the brain's primary inhibitory neurotransmitter, is increasing its influence, binding to receptors throughout your brain, and reducing neural activity in regions associated with arousal and anxiety. Adenosine, which has been accumulating in your brain throughout the day as a byproduct of neural activity, is reaching levels that promote sleepiness by inhibiting wake-promoting neurons and activating sleep centers. Serotonin levels are fluctuating in complex patterns that help regulate your sleep-wake cycle, while dopamine pathways are reducing their activity in areas associated with motivation and reward-seeking behavior. This neurochemical rebalancing is not merely a shutting down of brain function, but a carefully orchestrated transition to a different mode of neural operation, one optimized for memory consolidation, toxin clearance, and cellular repair. The neural pathways that mediate pain perception are undergoing interesting changes as sleep approaches. Natural opioid peptides like endorphins are being released in increased quantities, providing a gentle analgesic effect that allows minor aches and tensions to fade from awareness. This natural pain relief system helps explain why problems that seem significant during the day often feel less troublesome as you settle into bed. Temperature regulation centers in your hypothalamus are coordinating with your nervous system to promote the slight drop in core body temperature that facilitates sleep onset. Neural signals are redirecting blood flow toward your extremities, allowing heat to radiate away from your core. This thermal redistribution is why your hands and feet may feel warmer as you prepare for sleep, even as your overall body temperature decreases. The neural networks responsible for self-awareness and metacognition, those higher-order thinking processes that characterize conscious reflection, are beginning to reduce their activity. The default mode network, active during wakeful rest and self-referential thinking, starts to fragment and dissolve, contributing to the ego dissolution that marks the transition from waking consciousness to sleep. This neurological shift allows for the bizarre logic and fluid identity that characterize dreams. As the brain's normal constraints on narrative coherence and personal identity begin to loosen, the blood-brain barrier, that selective filter that protects your neural tissue from potentially harmful substances, is adjusting its permeability in subtle ways as sleep approaches. This specialized barrier, formed by tightly joined cells lining your brain's blood vessels, begins to allow increased passage of certain beneficial molecules while maintaining its protective function. Growth factors, immune system messengers, and nutrients that support neural repair gain enhanced access to brain tissue during sleep, contributing to the restorative processes that occur throughout the night. Your brain's electrical activity is shifting from the high-frequency, low-amplitude waves of waking consciousness to the slower, more synchronized patterns that characterize sleep preparation. Alpha waves, with their rhythmic 8 to 13 cycles per second, begin to dominate in regions of your brain associated with relaxed wakefulness. These electrical patterns, generated by millions of neurons firing in harmony, create the calm alertness that often accompanies the moments before sleep, a state where thoughts flow more freely and creative insights sometimes emerge. The neural circuitry that governs your circadian rhythms is fine-tuning its response to the absence of light. Specialized ganglion cells in your retina, distinct from those used for vision, continue to monitor ambient light levels and send signals directly to your suprachiasmatic nucleus. As these light-sensitive neurons detect the dimming environment, they reduce their inhibitory influence on melatonin production, allowing this sleep-promoting hormone to begin its gentle flood through your system. Mirror neurons, those fascinating cells that fire both when you perform an action and when you observe others performing the same action, are reducing their activity as social engagement decreases with approaching sleep. These neurons, crucial for empathy and social learning during waking hours, begin to quiet their responses as your brain shifts away from the interpersonal awareness that characterizes daytime consciousness. This reduction in mirror neuronality may contribute to the sense of social disconnection that often accompanies the transition towards sleep. The neural pathways involved in language processing are undergoing their own evening transformation. Broca's area and Wernicke's area, the brain regions responsible for speech production and comprehension, are reducing their activity as the need for verbal communication diminishes. This linguistic wind-down may explain why thoughts become less verbal and more imagistic as sleep approaches, and why the language of dreams often seems so different from waking speech patterns. Your brain's memory systems are preparing for one of sleep's most important functions: the consolidation of the day's experiences. The hippocampus, that seahorse-shaped structure, crucial for forming new memories, is beginning to replay the neural patterns associated with important events from your day. These memory traces will be strengthened and integrated during sleep, transferring from temporary storage in the hippocampus to more permanent repositories in the cortex. This process of memory consolidation transforms the raw experiences of the day into lasting knowledge and skills. The neural mechanisms of attention are gradually disengaging from the external world and turning inward. The attention networks that have been focused outward throughout the day, monitoring your environment for opportunities and threats, are beginning to lose their grip on external stimuli. This inward turning of attention allows for the introspective states that often accompany the moments before sleep, when memories surface spontaneously and the mind wanders through networks of association freed from the goal-directed focus of waking consciousness. Inhibitory interneurons throughout your brain are increasing their activity, creating a neural environment that favors rest over arousal. These specialized neurons, which make up roughly 20% of all brain cells, release GABA and other inhibitory neurotransmitters that calm the electrical activity of their neighbors. This widespread neural inhibition creates the conditions necessary for sleep onset, gradually silencing the brain networks that maintain waking consciousness, while preserving those essential for basic life functions. As this evening symphony of neural activity continues to unfold, your nervous system demonstrates its remarkable ability to transition between radically different modes of operation, while maintaining the essential functions that sustain life. The same neurons that created your thoughts and perceptions throughout the day are now preparing to generate the otherworldly experiences of dreams, while simultaneously coordinating the complex processes of memory consolidation and brain maintenance that will prepare you for tomorrow's awakening. Deep within your chest, a muscular pump, no larger than your fist, continues its tireless work, having beaten steadily since the 18th day of your embryonic development. Your heart, that remarkable four-chambered organ, is now adjusting its rhythm to match the peaceful transition your body is making towards sleep. As consciousness begins to fade and your breathing deepens, your cardiovascular system is orchestrating subtle but profound changes that will support the restorative processes of the night ahead. The cardiac muscle fibers that form the walls of your heart are unique in all of biology, combining the precision of skeletal muscle with the endurance of smooth muscle, creating a tissue that can contract forcefully and rhythmically without ever tiring. Each heartbeat originates in the sinoatrial node, a small cluster of specialized pacemaker cells in your right atrium that generates electrical impulses with the regularity of a biological metronome. As you settle into rest, these pacemaker cells are gradually slowing their firing rate, extending the intervals between heartbeats from perhaps every 0.8 of a second to a full second or more. This cardiac deceleration is not simply a passive response to decreased activity, but an active process coordinated by your autonomic nervous system. The vagus nerve, carrying parasympathetic signals from your brainstem, is releasing acetylcholine at nerve endings throughout your heart, causing the pacemaker cells to hyperpolarize and fire less frequently. Simultaneously, sympathetic nerve activity is diminishing, reducing the release of norepinephrine that would otherwise maintain your daytime heart rate. This dual neural influence creates the gentle cardiac slowdown that characterizes the transition towards sleep. Your heart's electrical conduction system is adapting to the requirements of nighttime rest with remarkable precision. The electrical impulse that begins in the sinoatrial node travels through specialized pathways in your atrial walls, causing these upper chambers to contract and push blood into the ventricles below. The signal then reaches the atrioventricular node, where it pauses briefly before continuing down the bundle of A's and into the Purkinje fibers that activate the powerful ventricular muscle. During sleep preparation, this entire conduction sequence becomes more stable and predictable, reducing the likelihood of irregular rhythms and promoting the steady, even heartbeat that supports peaceful rest. Blood pressure throughout your circulatory system is beginning its nighttime descent, dropping perhaps 10 to 20 millimeters of mercury as your heart rate slows and your blood vessels relax. This reduction occurs gradually and is carefully regulated by multiple mechanisms to ensure that vital organs continue to receive adequate perfusion. The baroreceptors in your carotid arteries and aortic arch, those pressure-sensitive nerve endings that monitor blood pressure moment by moment, are adjusting their sensitivity to accommodate the lower pressures of sleep, while maintaining their vigilance for any dangerous drops that might threaten organ function. The intricate network of blood vessels that carries life-sustaining fluid throughout your body is undergoing its own evening transformation. Arteries, those thick-walled vessels that carry oxygenated blood away from your heart, are relaxing their smooth muscle layers in response to parasympathetic stimulation and decreased sympathetic tone. This arterial dilation, particularly in vessels serving non-essential organs, allows blood flow to be redistributed toward areas involved in repair and restoration, such as your digestive system and immune organs. Your coronary arteries, the vessels that supply blood to your heart muscle itself, are dilating to ensure adequate perfusion of the cardiac tissue that will continue its work throughout the night. These specialized arteries, which branch directly from the aorta just above the heart valves, follow their own circadian rhythm, with blood flow increasing during the early hours of sleep to support the metabolic demands of the continuously contracting heart muscle. Venous return. The process by which blood travels back to your heart through the vast network of veins is being enhanced by the gentle pressure changes that occur with deep breathing and the rhythmic contractions of skeletal muscles as you shift position. Your veins, with their thinner walls and one-way valves, rely on these external forces to help push blood upward against gravity. As you lie down, the elimination of gravitational stress on your venous system allows blood to return to your heart more easily, contributing to the slight increase in stroke volume that often accompanies the transition to sleep. The capillary beds throughout your body, those microscopic networks where the actual exchange of nutrients and waste products occurs, are adjusting their permeability and flow patterns to match the metabolic demands of rest. Capillaries in your brain are maintaining high flow rates to support the intensive neural activity of sleep, while those in your skeletal muscles are reducing their perfusion as energy demands decrease. This selective redistribution of blood flow demonstrates the remarkable ability of your cardiovascular system to match supply with demand on a tissue-by-tissue basis. Your blood itself, that liquid tissue that connects every part of your body, is undergoing subtle changes in composition as sleep approaches. The concentration of stress hormones like cortisol and adrenaline is gradually decreasing, while levels of growth hormone and other anabolic factors are beginning to rise. Immune cells in your bloodstream are becoming more active, with natural killer cells and other defenders increasing their vigilance as your body shifts into its repair and maintenance mode. The oxygen carrying capacity of your blood remains constant, but the way oxygen is utilized by your tissues is changing. As metabolic rate decreases with approaching sleep, less oxygen is extracted from each unit of blood, allowing the venous blood returning to your heart to remain relatively rich in oxygen. This creates a reserve of oxygenation capacity that can be quickly mobilized if needed, while allowing your heart to work more efficiently at the slower rhythms of sleep. Red blood cells, those biconcave discs that make up nearly half the volume of your blood, are flowing through your circulatory system with the fluid grace that characterizes healthy circulation. Each of these cells, packed with hemoglobin molecules, carries oxygen from your lungs to your tissues and carbon dioxide back for elimination. During sleep, the production of new red blood cells in your bone marrow increases, taking advantage of the elevated growth hormone levels and reduced oxidative stress to manufacture fresh oxygen carriers. Platelets, those tiny cell fragments responsible for blood clotting, are adjusting their activity patterns as your circulation slows, while maintaining their essential function of preventing bleeding from minor vessel injuries. Platelets are becoming less sticky and aggregative, reducing the risk of inappropriate clot formation that could occur with the slower blood flow of sleep. This balance between hemostatic readiness and thrombotic prevention demonstrates the sophisticated regulation that governs your cardiovascular system. The lymphatic system, often called the body's second circulatory system, is increasing its activity as sleep approaches. This network of thin-walled vessels and lymph nodes, which runs parallel to your blood circulation, is responsible for collecting excess fluid from your tissues and returning it to your bloodstream. During sleep, when tissue repair and immune activity increase, lymphatic flow accelerates to handle the increased load of cellular debris and immune complexes that must be processed and eliminated. Lymphatic vessels in your brain, part of the recently discovered glymphatic system, are expanding their channels to allow increased flow of cerebrospinal fluid through brain tissue. This enhanced lymphatic drainage helps clear metabolic waste products that accumulate during waking hours, including proteins associated with neurodegenerative diseases. The improved lymphatic flow during sleep may explain why chronic sleep deprivation is associated with increased risk of cognitive decline and neurological disorders. Your spleen, that often forgotten organ tucked beneath your ribs on the left side, is releasing stored red blood cells into your circulation as sleep approaches. This splenic contraction, mediated by sympathetic nerve stimulation, increases your blood's oxygen carrying capacity, just as your body is preparing for the long hours of repair and restoration that lie ahead. The additional red blood cells will be available throughout the night to support the increased metabolic demands of tissue repair and immune function. The cardiovascular adaptations to sleep extend beyond simple changes in heart rate and blood pressure to encompass sophisticated adjustments in blood flow distribution, vessel reactivity, and fluid balance. Your circulatory system demonstrates its remarkable ability to support both the active metabolism of waking hours and the restorative processes of sleep, seamlessly transitioning between these different operational modes while maintaining the continuous perfusion that every cell in your body requires. As your cardiovascular river flows gently through the landscape of sleep, it carries not just oxygen and nutrients, but the very essence of life itself, connecting every part of your body in an intricate web of circulation that will continue its vital work long after consciousness fades and dreams begin their mysterious dance. With each gentle breath you take, your respiratory system orchestrates one of life's most fundamental rhythms, a tide of air that flows in and out of your lungs with the regularity of ocean waves against a peaceful shore. As you settle into rest, this breathing pattern is undergoing a gradual transformation, shifting from the variable rhythms of conscious activity to the deeper, more regular respirations that will sustain you throughout the night. Your respiratory system, extending from your nostrils to the tiny air sacs deep within your lungs, is preparing for the long hours of gentle gas exchange that lie ahead. The rhythm of your breathing originates in the medulla oblongata, that ancient part of your brainstem where the most fundamental life functions are controlled. Here, in clusters of neurons called the pre-Boxinger complex, your respiratory rhythm is generated with the same automaticity that governs your heartbeat. As sleep approaches, these neural pacemaker cells are adjusting their firing pattern, gradually slowing the respiratory rate from perhaps 15 to 20 breaths per minute to the deeper, slower pattern of approaching sleep, where each breath cycle may extend to 6 or 7 seconds. Your diaphragm, that dome-shaped muscle that forms the floor of your chest cavity, is the primary engine of breathing. As you transition towards sleep, this remarkable muscle is finding its rhythm of peaceful expansion and contraction. During inspiration, the diaphragm contracts and flattens, creating negative pressure within your chest that draws air into your lungs with effortless grace. The movement is so smooth and automatic that it requires no conscious thought, yet it involves precise coordination between neural control centers in the muscular architecture of breathing. The intercostal muscles, those small muscles that run between your ribs, are working in harmony with your diaphragm to create the gentle bellows action that moves air in and out of your lungs. During quiet breathing, as you experience now, these muscles make only subtle adjustments to rib position, allowing the diaphragm to do most of the work. This economical breathing pattern minimizes energy expenditure while maintaining adequate ventilation, demonstrating the efficiency that characterizes all biological systems at rest. As air enters through your nose or mouth, it begins a journey through increasingly specialized passages designed to condition it for gas exchange. Your nasal passages, lined with ciliated epithelium and richly supplied with blood vessels, warm and humidify the incoming air while filtering out particles and potential pathogens. The turbinates, those curved structures within your nasal cavity, create turbulent airflow that enhances contact between air and the conditioning surfaces, ensuring that by the time air reaches your lungs, it is at body temperature and fully saturated with water vapor. The mucus that lines your respiratory passages serves as both filter and transport system, trapping particles and microorganisms while moving them upward through the coordinated beating of millions of cilia. This mucociliary escalator works continuously, clearing your airways of debris and maintaining the pristine environment necessary for efficient gas exchange. During sleep, this cleaning system becomes even more active, taking advantage of the reduced airflow to perform intensive maintenance of your respiratory passages. Your larynx, housing the vocal cords that create speech and song during waking hours, is now relaxed and open, allowing air to pass through with minimal turbulence. The epiglottis, that cartilaginous flap that protects your airway during swallowing, is positioned to keep your respiratory passage clear while you sleep. The muscles that control these structures are under the influence of your autonomic nervous system, which maintains their proper positioning without conscious effort throughout the night. The trachea, your main airway, extends downward from your larynx like a flexible tube, reinforced with horseshoe-shaped rings of cartilage. These rings keep your airway open while allowing the flexibility necessary for breathing and head movement. The smooth muscle at the back of each ring can adjust the diameter of your trachea slightly, fine-tuning airflow resistance in response to your body's needs. During sleep, this smooth muscle relaxes, creating the most open pathway possible for the gentle flow of air. As your trachea branches into the bronchi and then into progressively smaller bronchioles, the architecture of your respiratory system resembles an inverted tree, with your trachea as the trunk and the smallest airways as delicate twigs, reaching into every corner of your lungs. This branching pattern, repeated through approximately 23 generations of division, creates an enormous surface area for gas exchange, while maintaining efficient air distribution throughout your lung tissue. The bronchioles, those smallest airways that lead directly to the gas-exchanging regions of your lungs, are lined with smooth muscle that can adjust their diameter in response to various stimuli. During sleep, these muscles relax under parasympathetic influence, opening the airways to their maximum diameter and reducing the work of breathing. This bronchodilation ensures that air can flow freely to all regions of your lungs, even at the reduced breathing rates characteristic of sleep deep. Within your lungs, approximately 300 million tiny air sacs called alveoli create the vast surface area where the magic of gas exchange occurs. If spread flat, these alveoli would cover an area roughly the size of a tennis court, yet they are packed efficiently within the confines of your chest cavity. Each alveolus is surrounded by a dense network of capillaries, creating an interface where oxygen and carbon dioxide can move freely between air and blood. The walls of your alveoli are incredibly thin, measuring only about half a micrometer in thickness, roughly 1/100th the width of a human hair. This minimal barrier between air and blood allows gases to diffuse rapidly across the respiratory membrane, driven by the simple physical process of moving from areas of high concentration to areas of low concentration. Oxygen dissolves into the thin film of fluid that lines each alveolus and then crosses into the bloodstream, while carbon dioxide moves in the opposite direction for elimination. Surfactant, a remarkable mixture of phospholipids and proteins, produced by specialized cells in your alveoli, reduces surface tension and prevents these tiny air sacs from collapsing during expiration. This biological detergent is essential for efficient breathing, reducing the work required to inflate your lungs with each breath. During sleep, surfactant production continues, maintaining the stability of your alveoli throughout the long hours of gentle breathing that lie ahead. The pleural membranes that surround your lungs create a sealed space, filled with a thin layer of pleural fluid that lubricates the movement of your lungs within your chest cavity. This pleural space maintains a slightly negative pressure that helps keep your lungs expanded and allows them to follow the movements of your chest wall during breathing. As you breathe peacefully, these membranes slide smoothly over each other, ensuring that your lungs can expand and contract without friction or discomfort. Gas exchange in your lungs operates on the principle of passive diffusion, requiring no energy expenditure beyond the work of moving air in and out of your respiratory system. Oxygen molecules, driven by their concentration gradient, dissolve into your bloodstream where they bind to hemoglobin in your red blood cells. Meanwhile, carbon dioxide, a waste product of cellular metabolism, moves from your blood into your alveoli for elimination during expiration. This continuous exchange occurs with each breath, maintaining the precise balance of gases necessary for life. Your respiratory control system adjusts breathing rate and depth in response to changes in blood chemistry, particularly the levels of carbon dioxide and oxygen. Chemoreceptors in your brainstem and in your carotid and aortic bodies monitor these levels continuously, sending signals to your respiratory control centers to increase or decrease ventilation as needed. During sleep, this system becomes the primary regulator of breathing, maintaining adequate gas exchange while allowing your conscious mind to rest. The voice box or larynx undergoes its own transformation as sleep approaches. The vocal cords, those delicate folds of tissue that vibrate to create speech and song, are relaxing into their resting position. The intricate muscles that control pitch and volume are releasing their daytime tensions, allowing the larynx to settle into the configuration that will produce the gentle sounds of sleeping breath. Occasionally, these relaxed tissues may vibrate slightly with the passage of air, creating the soft sounds of peaceful sleep. Temperature regulation through your respiratory system becomes particularly important as sleep approaches. The evaporation of water from your respiratory passages carries away heat, contributing to the slight drop in core body temperature that signals your brain to initiate sleep. This evaporative cooling is enhanced by the increased humidity of the air you exhale, which carries away both heat and moisture with each breath. Your respiratory muscles, having worked tirelessly throughout the day to maintain ventilation, are now settling into the efficient, economical pattern of sleep. The accessory muscles of breathing, including those in your neck and between your ribs, are relaxing and allowing your diaphragm to assume the primary responsibility for ventilation. This shift to diaphragmatic breathing is not only more efficient, but also activates the parasympathetic nervous system, promoting the relaxation response that facilitates sleep. The coordination between your respiratory and cardiovascular systems becomes even more evident as sleep approaches. Your heart rate naturally synchronizes with your breathing pattern, accelerating slightly during inspiration and slowing during expiration in a phenomenon known as respiratory sinus arrhythmia. This coupling of breathing and heart rate optimizes the efficiency of gas transport and demonstrates the intimate connection between these two vital systems. As your respiratory tide continues its gentle ebb and flow, each breath carries away the metabolic waste of the day, while bringing in the fresh oxygen that will sustain your body's overnight repair and restoration. This ancient rhythm, as old as life itself, will continue throughout the night, maintaining the delicate balance of gases that allows every cell in your body to function while your conscious mind travels through the mysterious landscapes of sleep and dreams. As consciousness fades and your body settles into the deeper rhythms of approaching sleep, your digestive system is far from resting. Instead, it is embarking on its own nocturnal journey, a carefully orchestrated sequence of processes that will continue throughout the night. While your mind drifts toward dreams, your gastrointestinal tract maintains its patient work of breaking down the day's nourishment and preparing your body for tomorrow's awakening. Your stomach, that muscular sac, nestled beneath your ribs, is engaged in its own rhythmic dance. As sleep approaches, the smooth muscle fibers in its walls are contracting in slow, coordinated waves that gently churn any remaining food from your evening meal. These peristaltic movements mix digestive juices with food particles, while gradually moving the contents toward your small intestine. The gastric pits that line your stomach wall are secreting digestive enzymes, hydrochloric acid, and protective mucus. Pepsinogen is being converted to its active form, pepsin, by the acidic environment, beginning the systematic breakdown of proteins from your last meal. Chief cells produce this pepsinogen, while parietal cells generate the hydrochloric acid necessary for digestion. As sleep deepens, your stomach's production of gastric acid follows a natural circadian rhythm, typically decreasing during the night hours while maintaining enough activity to process any remaining food. This reduction is mediated by your vagus nerve, which carries parasympathetic signals that modulate digestive activity based on your body's overall state of rest. Your small intestine, that remarkable 20-foot coiled tube where most nutrient absorption occurs, continues its methodical work throughout the night. The muscular walls contract in coordinated waves that propel partially digested food slowly along its length. These contractions, known as migrating motor complexes, occur in cycles roughly every 90 to 120 minutes, sweeping through your intestines like a slow cleaning wave. The villi and microvilli that line your small intestine are actively transporting nutrients from your intestinal contents into your bloodstream. Amino acids from proteins, simple sugars from carbohydrates, and fatty acids from fats are crossing the intestinal barrier and entering your portal circulation, bound for your liver, where they will be processed according to your body's needs. Digestive enzymes from your pancreas work in harmony with bile from your liver to break down complex molecules. Lipases split fats into fatty acids and glycerol, proteases cleave proteins into amino acids, and amylases convert starches into simple sugars. This enzymatic orchestra operates with remarkable efficiency, ensuring that nutrients consumed hours ago are systematically extracted and made available to your cells. Your large intestine is engaged in its own essential work as you transition towards sleep. Here, the focus shifts from nutrient absorption to the reclamation of water and electrolytes from the remaining digestive contents. The colon slowly moves material along through powerful but infrequent contractions, allowing time for water absorption while compacting the remaining waste. The bacterial ecosystem that inhabits your large intestine becomes particularly active during the nighttime hours. These beneficial microorganisms are fermenting undigested carbohydrates, producing short-chain fatty acids that nourish the cells lining your colon while generating vitamins like biotin and vitamin K that your body cannot produce on its own. Your liver, that remarkable metabolic powerhouse weighing approximately 3 pounds, is perhaps the busiest organ in your body as sleep approaches. Located in the upper right portion of your abdomen, Your liver is simultaneously performing hundreds of different biochemical processes. As you settle into rest, your liver shifts into its nocturnal mode, emphasizing detoxification, protein synthesis, and metabolic regulation. The hepatocytes that make up roughly 80% of your liver's mass are working to process nutrients absorbed from your digestive tract. Glucose from your evening meal is being converted into glycogen for storage, creating a readily available energy reserve that can be mobilized when your blood sugar levels drop during sleep. This process of glycogenesis is carefully regulated by insulin and other hormones. Simultaneously, your liver is engaged in gluconeogenesis, creating new glucose from non-carbohydrate sources like amino acids and glycerol. This glucose production becomes increasingly important as the night progresses, and your body's glycogen stores are gradually depleted. The ability to maintain stable blood sugar levels during sleep is crucial for proper brain function. Your liver's detoxification systems operate at peak efficiency during the nighttime hours. The cytochrome P450 enzyme systems are metabolizing medications, environmental toxins, and metabolic waste products that have accumulated throughout the day. This detoxification process involves making toxins more water-soluble, then conjugating them with other molecules to facilitate their elimination. Bile production continues throughout the night. This complex mixture of bile salts, cholesterol, phospholipids, and bilirubin is being synthesized continuously and either released directly into your small intestine or stored in your gallbladder. Bile salts are essential for fat digestion, emulsifying dietary fats into smaller droplets that can be processed by pancreatic enzymes. Your pancreas serves dual roles as both an endocrine and exocrine organ. As sleep approaches, the exocrine portion reduces its secretion of pancreatic juice while maintaining enough activity to support ongoing digestion. The acinar cells that produce digestive enzymes follow the natural circadian rhythm that coordinates digestive function with your sleep-wake cycle. The endocrine function of your pancreas becomes particularly important during sleep, as your body works to maintain stable blood glucose levels. Beta cells within the islets of Langerhans monitor your blood sugar continuously and release insulin when levels rise, while alpha cells produce glucagon when glucose levels drop too low. This delicate hormonal balance ensures that your brain and other glucose-dependent tissues receive adequate fuel throughout the night. During sleep, your pancreas must maintain blood glucose stability during the longest fasting period of each 24-hour cycle. As glycogen stores in your liver are gradually depleted, your pancreas adjusts its hormone production to encourage gluconeogenesis and the mobilization of alternative fuel sources like fatty acids. Your gallbladder, a small organ tucked beneath your liver, is concentrating and storing bile produced by your liver during the nighttime hours. Between meals, bile flows from your liver into your gallbladder, where it is concentrated by the removal of water and electrolytes. This concentrated bile will be available for rapid release when you eat your next meal. As you drift deeper into sleep, your digestive system continues its essential work with quiet efficiency, processing the nutrients that will fuel tomorrow's activities, while maintaining the delicate metabolic balance necessary for health and vitality. This nocturnal digestive symphony operates largely below the threshold of consciousness, yet it is every bit as vital as the more obvious functions of breathing and circulation. Deep within your body, a sophisticated network of chemical messengers is orchestrating one of the most remarkable transformations of each 24-hour cycle. Your endocrine system, composed of specialized glands scattered throughout your anatomy, is shifting into its nocturnal mode of operation as sleep approaches. These ductless glands, working in perfect coordination with your nervous system, are adjusting their hormone production to support the restorative processes that will unfold throughout the night. The hypothalamus, nestled deep within your brain and no larger than an almond, serves as the master conductor of this hormonal symphony. This remarkable structure contains your body's primary biological clock, the suprachiasmatic nucleus, which has been tracking the passage of light and darkness throughout the day. As evening settles around you, this internal timekeeper is initiating a cascade of hormonal changes that will prepare every cell in your body for the hours of rest ahead. Your pituitary gland, often called the master gland, dangles from your hypothalamus like a tiny grape suspended by a delicate stalk, divided into anterior and posterior regions. This pea-sized structure is responding to signals from your hypothalamus by adjusting its own hormone production. The posterior pituitary is releasing antidiuretic hormone, which will help your kidneys conserve water during the long hours without fluid intake, while the anterior pituitary is preparing to release growth hormone in carefully timed pulses throughout the night. Growth hormone, perhaps the most important anabolic signal your body produces, follows a dramatic circadian rhythm that peaks during the deep sleep phases. As you transition from wakefulness to sleep, your pituitary gland is preparing to release this powerful hormone in surges that will stimulate protein synthesis, promote tissue repair, and support the cellular regeneration that occurs during rest. Children and adolescents experience particularly robust growth hormone release during sleep, explaining why adequate rest is so crucial for proper development. The pineal gland, that mysterious structure once called the third eye, is beginning its most active phase as darkness falls. This tiny pinecone-shaped organ, located deep within your brain, is responding to the absence of light by dramatically increasing its production of melatonin. This hormone, synthesized from the neurotransmitter serotonin, acts as a chemical signal of nighttime, informing every cell in your body that sleep is approaching, and metabolic processes should shift accordingly. Melatonin levels in your bloodstream will rise steadily throughout the evening, reaching peak concentrations in the middle of the night before gradually declining toward morning. This hormonal tide helps synchronize your circadian rhythms, promotes sleepiness, and coordinates the timing of numerous physiological processes. The melatonin surge also has antioxidant properties, helping to protect your cells from oxidative damage during the vulnerable hours of sleep. Cortisol, often called the stress hormone, is following its own distinct circadian pattern as your body prepares for sleep. Produced by the outer layer of your adrenal glands, cortisol levels are gradually declining from their daytime peaks, creating the hormonal environment necessary for restful sleep. This reduction in cortisol is essential for proper sleep onset, as elevated levels of this hormone would maintain alertness and prevent the relaxation necessary for rest. The relationship between cortisol and sleep is bidirectional and carefully regulated. During the night, cortisol levels reach their lowest point, typically occurring in the first half of the sleep period. This hormonal nadir allows for optimal immune function, tissue repair, and memory consolidation. Toward morning, cortisol levels will begin to rise again, preparing your body for awakening and the metabolic demands of a new day. Your adrenal glands, those triangular structures perched atop your kidneys like tiny caps, are adjusting their entire hormonal output as sleep approaches. In addition to cortisol, these glands produce aldosterone, which helps regulate sodium and potassium balance, and small amounts of sex hormones that contribute to overall hormonal balance. The adrenal medulla, the inner portion of these glands, is reducing its production of adrenaline and noradrenaline, allowing your sympathetic nervous system to wind down. The coordination between your hypothalamic pituitary adrenal axis demonstrates the remarkable integration that characterizes endocrine function during sleep. Corticotropin-releasing hormone from your hypothalamus stimulates the pituitary to release adrenocorticotropic hormone, which in turn regulates cortisol production by your adrenal glands. This three-tier system ensures precise control over cortisol levels throughout the day and night. Your thyroid gland, located in your neck just below your Adam's apple, is adjusting its metabolic control systems as sleep approaches. This butterfly-shaped gland produces thyroid hormones that regulate your metabolic rate, and their levels follow a subtle circadian rhythm. Thyroid-stimulating hormone from your pituitary gland shows peak levels during the night, while the thyroid hormones themselves, T3 and T4, reach their lowest concentrations during sleep. This nocturnal reduction in thyroid hormone activity contributes to the decrease in metabolic rate that characterizes sleep. Your core body temperature drops slightly, your heart rate slows, and your energy expenditure decreases, all partially mediated by reduced thyroid hormone action. This metabolic downshift allows your body to redirect energy from basic maintenance functions toward repair and restoration processes. The calcitonin produced by your thyroid gland also follows circadian patterns, with levels typically rising during sleep. This hormone works to regulate calcium levels in your blood, promoting calcium deposition in bones during the hours when physical stress on the skeleton is minimal. The coordination between calcitonin and parathyroid hormone ensures that calcium homeostasis is maintained throughout the sleep period. Your parathyroid glands, 4 tiny structures embedded in the back of your thyroid, are fine-tuning calcium regulation as your body prepares for the long fast of sleep. Parathyroid hormone levels show complex circadian variations, generally increasing during the night, to maintain appropriate calcium levels in your blood, despite the absence of dietary calcium intake. This hormone stimulates calcium absorption from your bones and kidneys, ensuring that vital cellular processes that depend on calcium can continue uninterrupted. The intricate dance between calcitonin and parathyroid hormone illustrates the precision with which your endocrine system maintains homeostasis during sleep. Calcium is essential for muscle contraction, nerve transmission, and blood clotting, so its levels must be carefully regulated even during the hours when you are not consuming calcium-rich foods. Temperature regulation, one of the most important physiological changes during sleep onset, orchestrated by a complex interplay of hormones. Your hypothalamus is adjusting your body's thermostat, allowing your core temperature to drop by 1 to 2 degrees Fahrenheit. This temperature reduction is mediated by changes in thyroid hormones, growth hormone-releasing hormone and melatonin, all working together to create the cooler internal environment that facilitates sleep onset and maintenance. The slight drop in body temperature that occurs during sleep serves multiple purposes. It reduces metabolic demands, conserves energy, and appears to be necessary for optimal sleep quality. The temperature regulation during sleep is so precise that even small disruptions can interfere with sleep quality, highlighting the importance of maintaining appropriate bedroom temperatures for restful sleep. Prolactin, traditionally associated with lactation in nursing mothers, actually plays important roles in sleep regulation for all individuals. Prolactin levels rise significantly during sleep, reaching peak concentrations in the early morning hours. This hormone appears to promote REM sleep and may contribute to the immune system changes that occur during rest. The surge in prolactin during sleep is one of the most reliable hormonal markers of sleep onset and maintenance. Your endocrine system's transition into sleep mode represents one of the most sophisticated examples of biological timing in nature. The precise coordination of multiple hormones, each following its own circadian rhythm while integrating with the patterns of others, creates the optimal internal environment for rest and restoration. As you settle into sleep, this chemical orchestra is beginning its nightly performance, a hormonal symphony that will continue throughout the dark hours, ensuring that you wake refreshed and restored for the day ahead. Enveloping your entire body like a living blanket, your skin serves as the ultimate boundary between your internal world and the external environment. As you settle into rest, this remarkable organ, the largest in your body, is undergoing its own transformation in preparation for the restorative hours ahead. Your integumentary system, comprising skin, hair, nails, and various glands, is shifting into its nocturnal mode of operation, emphasizing repair, renewal, and protection throughout the night. Your skin, covering approximately 20 square feet and weighing roughly 8 pounds, is far more than a simple protective covering. It is a dynamic, living tissue composed of multiple layers, each with specialized functions that become particularly important during sleep. As consciousness fades, your skin is preparing for its most important work period, the hours when cellular renewal and repair reach their peak activity. The epidermis, that outermost layer measuring only about as thick as a sheet of paper, is engaged in continuous renewal that accelerates during sleep. The basal layer contains stem cells that divide throughout the night, producing new keratinocytes that will gradually migrate upward through the skin layers over 30 days. This cellular renewal is enhanced during sleep, when growth hormone levels peak and repair mechanisms are most active. As new skin cells form in the basal layer, they begin their journey toward the surface, gradually changing structure and composition. They accumulate keratin, a tough protein providing strength and water resistance, while losing their nuclei and other cellular organelles. By the time they reach your skin's surface, these cells have transformed into flat, dead scales forming the protective stratum corneum, your body's first line of defense. The dermis, lying beneath your epidermis, contains the structural framework that gives your skin its strength, elasticity, and resilience. Composed of collagen and elastin fibers woven in a complex matrix, the dermis houses blood vessels, nerve endings, hair follicles, and glands. During sleep, increased blood flow brings additional nutrients and oxygen to support intensive repair and maintenance activities. Fibroblasts within your dermis work overtime during sleep, synthesizing new collagen and elastin fibers to replace those damaged by daily wear and ultraviolet radiation. This nocturnal repair work is stimulated by growth hormone and other factors that peak during sleep, making adequate rest essential for maintaining healthy skin. The old saying about beauty sleep has a solid foundation in skin repair biochemistry. Temperature regulation through your skin becomes particularly sophisticated as sleep approaches. Blood vessels in your dermis are dilating in response to signals from your hypothalamus, allowing warm blood to flow near the surface where heat can radiate into the environment. This vasodilation creates the slight drop in core body temperature necessary for sleep onset, demonstrating how your skin participates actively in sleep regulation. Your skin's sensory functions adapt to sleep requirements while maintaining vigilance for dangerous stimuli. Thousands of nerve endings throughout your skin are adjusting their sensitivity, becoming less responsive to light touch and routine stimuli, while maintaining their ability to detect pain, extreme temperatures, or other danger signals. This selective sensory dampening allows peaceful sleep despite contact with bedding while preserving protective reflexes. Your hair follicles, those tube-like structures extending deep into your dermis, follow their own circadian rhythms as night falls. Hair growth occurs in cycles, with periods of active growth alternating with phases of rest and eventual hair loss. Many hair follicles enter their most active growth phase during sleep, when cellular division rates are highest and growth factors are most abundant. The hair shaft itself, composed of dead, keratinized cells, provides insulation and protection for your scalp and other areas. On your scalp, hair helps maintain stable temperature by trapping air close to your skin. The sebaceous glands, associated with each hair follicle, produce sebum, an oily substance that lubricates both hair and skin while providing antimicrobial protection. During sleep, sebum production follows its own rhythm, generally decreasing from daytime levels, but continuing at a rate sufficient to maintain the protective lipid layer on your skin surface. This natural oil helps prevent water loss, while creating an environment that discourages harmful bacteria and fungi growth. Sebum includes triglycerides, wax esters, and free fatty acids that work together to maintain skin health. Your fingernails and toenails, composed of specialized keratin, similar to hair, grow continuously throughout the night. Nail growth occurs in the nail matrix, located beneath the visible nail plate, where new keratin cells are constantly produced and pushed forward. Fingernails grow at approximately 3 mm per month, while toenails grow more slowly at about 1 mm per month. Nail formation requires adequate nutrition, particularly proteins and vitamins, which is why nail health often reflects overall nutritional status. During sleep, when growth hormone levels are elevated and cellular repair processes are most active, nail growth rates may increase slightly. The cuticle, that thin layer overlapping the base of your nail, serves as a protective seal preventing bacteria from entering the nail matrix. The lunula, that white, crescent-shaped area visible at the base of your nails, represents the visible portion of the nail matrix where new nail cells are being formed. This area appears white because underlying blood vessels are less visible through the thicker tissue of the actively growing nail matrix. The health and appearance of your lunula can provide insights into your overall health. Keratin production throughout your integumentary system reaches peak activity during sleep, when protein synthesis is enhanced by elevated growth hormone levels. This tough, fibrous protein provides the structural foundation for your hair, nails, and the outer layer of your skin. The process of keratinization involves the gradual transformation of living cells into dead, protective structures filled with keratin filaments. Your skin's pH balance, typically slightly acidic at around 5.5, helps maintain the health of your skin's microbiome while inhibiting pathogenic organisms. During sleep, this acid mantle may become slightly more acidic as your skin's metabolism shifts and sebaceous gland activity changes. This pH regulation is crucial for maintaining your skin's barrier function and preventing infection. Sweat glands throughout your skin continue their important work of temperature regulation during sleep, though their activity typically decreases from daytime levels. Green sweat glands produce watery sweat that helps cool your body through evaporation. POC. Sweat glands, located primarily in your armpits and groin area, produce a different type of sweat that becomes odorous when broken down by skin bacteria. The circadian rhythm of sweating shows interesting variations, with most people experiencing reduced sweating during early sleep hours, followed by potential increases during REM sleep phases, when body temperature regulation becomes less precise. This pattern helps maintain optimal body temperature throughout the night, while minimizing fluid loss during hours when water intake is not possible. As you drift deeper into sleep, your integumentary sanctuary continues its vital work of protection, regulation, and renewal. This living boundary between your internal world and the external environment demonstrates the remarkable ability of biological systems to maintain essential functions while adapting to the changing demands of rest and restoration. Throughout the night, your skin will continue its patient work of cellular renewal and repair, ensuring that you wake with a refreshed and restored protective barrier ready to face the challenges of a new day. Deep within your abdomen, Two remarkable organs are working with quiet efficiency to maintain the delicate chemical balance that sustains life. Your kidneys, each about the size of your fist, are performing one of the most sophisticated filtration processes in the biological world. As you settle into sleep, these bean-shaped structures are adjusting their function to meet the unique demands of the night hours. When fluid intake ceases but the need for waste removal and electrolyte balance continues, your kidneys filter approximately 50 gallons of blood each day through an intricate network of microscopic structures called nephrons. Each kidney contains approximately 1 million of these functional units, tiny biological factories that sort through your blood with remarkable precision, retaining what your body needs while eliminating what it does not. As sleep approaches, this filtration process is subtly adjusting its parameters, preparing for the hours ahead when conservation of water becomes particularly important. The nephron, that fundamental unit of kidney function, demonstrates biological engineering at its finest. Each nephron begins with a glomerulus, a tiny cluster of capillaries where the initial filtration of blood occurs. Here, water, electrolytes, glucose, amino acids, and waste products are filtered from your blood under pressure, creating a filtrate that will be processed as it travels through the nephron's tubular system. During sleep, the filtration rate decreases slightly as blood pressure drops and renal blood flow is reduced. As the filtrate moves through the proximal tubule, approximately 65% of the filtered sodium and water are reabsorbed back into your bloodstream. This reabsorption process is enhanced during sleep when antidiuretic hormone levels rise, signaling your kidneys to conserve water more aggressively. The cells lining the proximal tubule work tirelessly throughout the night to reclaim valuable substances that your body cannot afford to lose. The loop of Henle creates a concentration gradient that allows your kidneys to produce urine far more concentrated than your blood. This remarkable mechanism enables your body to eliminate waste products while conserving precious water, a capability that becomes particularly important during the overnight fast when no fluids are being consumed. The ascending limb actively pumps sodium and chloride out of the filtrate while remaining impermeable to water. The distal tubule and collecting duct system represent the final stages of urine formation, where precise adjustments determine the final concentration and composition of your urine. Here, under the influence of hormones like aldosterone and antidiuretic hormone, your kidneys make critical decisions about how much sodium, potassium, and water to retain or eliminate. During sleep, these tubular segments work to concentrate your urine and minimize fluid loss. Antidiuretic hormone, released from your posterior pituitary gland, exerts its primary effect on the collecting ducts of your nephrons. This hormone increases the permeability of the collecting duct to water, allowing more water to be reabsorbed from the urine back into your bloodstream. The result is more concentrated urine and conservation of body water, a process that becomes particularly important during the long hours of sleep, when fluid replacement is not possible. Your bladder. That expandable muscular sac, located in your lower pelvis, serves as a temporary storage reservoir for the urine produced by your kidneys. Composed of smooth muscle fibers arranged in multiple layers, your bladder can stretch to accommodate varying volumes of urine, while maintaining relatively low internal pressure. During sleep, your bladder's capacity for expansion becomes particularly important as urine production continues throughout the night. But opportunities for emptying are limited. The detrusor muscle, which forms the main body of your bladder wall, is capable of remarkable expansion without significant increases in pressure. This accommodation is possible because of the unique properties of smooth muscle and the specialized arrangement of muscle fibers within the bladder wall. As your bladder gradually fills during sleep, stretch receptors in the wall monitor the degree of distension and send signals to your spinal cord and brain about the bladder's fullness. The neural control of bladder function involves a complex interplay between your autonomic nervous system and higher brain centers. During sleep, the sympathetic nervous system helps maintain bladder relaxation and urethral sphincter contraction, promoting urine storage rather than elimination. The parasympathetic system, which would normally stimulate bladder contraction, is suppressed during sleep to prevent inappropriate voiding. This neural coordination ensures that sleep is not unnecessarily interrupted. The internal urethral sphincter, composed of smooth muscle and under involuntary control, remains contracted during sleep to prevent urine leakage. This sphincter works in coordination with the external urethral sphincter, which is composed of skeletal muscle and under voluntary control. Together, these sphincters create a dual-gated system that maintains continence during sleep, while allowing for conscious control of urination when awake. Your kidney's role in maintaining acid-base balance becomes particularly important during sleep. When respiratory patterns change and metabolic processes shift, the kidneys can excrete excess acid or retain bicarbonate, as needed to maintain blood pH within the narrow range necessary for optimal cellular function. This buffering capacity operates continuously, making subtle adjustments throughout the night to compensate for metabolic changes that occur during different phases of sleep. Electrolyte balance, particularly the regulation of sodium, potassium, and chloride, is carefully maintained by your kidneys throughout the sleep period. Sodium retention or excretion is primarily controlled by the renin-angiotensin-aldosterone system, which responds to changes in blood pressure, blood volume, and sodium concentration. During sleep, when blood pressure typically decreases, your kidneys adjust sodium handling to maintain appropriate fluid balance. The renin-angiotensin-aldosterone system represents one of the most important hormonal pathways for regulating blood pressure and fluid balance. When blood pressure drops or blood volume decreases, specialized cells in your kidneys release renin, an enzyme that initiates a cascade, ultimately leading to the production of angiotensin and the release of aldosterone. This system is particularly active during sleep when postural changes and decreased activity can affect blood pressure. Your kidneys also serve as endocrine organs, producing several important hormones that affect other body systems. Erythropoietin stimulates red blood cell production in your bone marrow in response to low oxygen levels. Calcitriol, the active form of vitamin D, is synthesized in the kidneys and plays crucial roles in calcium absorption and bone health. These endocrine functions continue throughout sleep, contributing to the overall hormonal environment that supports rest and recovery. As the night progresses and your body continues its work of cellular repair and restoration, your urinary system maintains its vigilant watch over the chemical composition of your internal environment. The concentrated urine that accumulates in your bladder throughout the night represents the end product of countless molecular decisions made by your nephrons, each one contributing to the maintenance of the precise conditions necessary for life. When morning comes and you awaken, your kidneys will have successfully navigated the challenges of the overnight fast, maintaining perfect chemical balance while conserving the water and electrolytes essential for another day of health and vitality. Within the quiet depths of your body, specialized organs are following ancient rhythms that connect you to the fundamental cycles of life itself. Your reproductive system, even during the peaceful hours of sleep, continues its intricate work of cellular renewal, hormone production, and the maintenance of biological processes that have evolved over millions of years. As you rest, these organs respond to the same circadian signals that govern your sleep-wake cycle, demonstrating the profound interconnection between rest and the preservation of life's greatest mystery. Your reproductive organs are governed by complex hormonal rhythms that ebb and flow throughout each 24-hour period. These hormones, produced by your reproductive glands and your brain's hypothalamus and pituitary gland, follow patterns refined by evolutionary pressures to optimize reproductive health. During sleep, when many other body systems are reducing their activity, your reproductive system maintains its essential work of hormone production and cellular maintenance. The hypothalamic pituitary gonadal axis represents one of the most sophisticated hormonal control systems in your body. Your hypothalamus releases gonadotropin-releasing hormone in carefully timed pulses that stimulate your pituitary gland to produce luteinizing hormone and follicle-stimulating hormone. These hormones then travel through your bloodstream to your reproductive organs, where they regulate the production of sex hormones and the development of reproductive cells. This hormonal cascade continues throughout the night, following circadian patterns that coordinate reproductive function with your body's overall biological rhythms. In males, testosterone production follows a distinct circadian pattern, with levels typically peaking in the early morning hours and gradually declining throughout the day. During sleep, particularly during the deeper phases, testosterone production increases, reaching its highest concentrations just before awakening. This nocturnal surge supports not only reproductive function, but also muscle protein synthesis, bone density maintenance, and overall metabolic health. The testes, housed within the scrotum outside the main body cavity, maintain their optimal temperature for sperm production throughout the night. This external positioning, which keeps the testes approximately 2 degrees cooler than core body temperature, is essential for spermatogenesis, the process of sperm cell development. During sleep, when core body temperature drops slightly, the temperature differential that supports sperm production is maintained through natural thermoregulatory mechanisms, Spermatogenesis itself is a continuous process that takes approximately 74 days from start to finish. Within the seminiferous tubules of the testes, primitive germ cells are constantly dividing and differentiating into mature sperm cells. This process continues throughout the night, supported by the hormonal environment created by nighttime testosterone production and the optimal temperature conditions maintained during sleep. In females, the reproductive system follows more complex cyclical patterns that interact with daily circadian rhythms in sophisticated ways. The menstrual cycle, typically lasting 28 days, is coordinated by the same hypothalamic pituitary system that governs daily hormone fluctuations. During sleep, the production of reproductive hormones continues according to both daily and monthly cycles, creating a multidimensional pattern of hormonal regulation. Estrogen and progesterone, the primary female reproductive hormones, show daily variations that are superimposed on their monthly cyclical changes. During the first half of the menstrual cycle, when estrogen levels are rising, the hormone's peak concentrations often occur during the late afternoon and evening hours. During the second half of the cycle, progesterone becomes the dominant hormone, and its levels typically peak during the nighttime hours, contributing to the slight increase in body temperature that characterizes the luteal phase. The ovaries, those almond-shaped organs nestled within the pelvic cavity, are constantly engaged in the process of follicle development and hormone production. Each ovary contains thousands of follicles, each housing an immature egg cell surrounded by supportive cells. During sleep, follicle-stimulating hormone and luteinizing hormone continue to stimulate follicle development, supporting the growth of the dominant follicle that will eventually release its egg during ovulation. The intricate process of follicle development, known as folliculogenesis, occurs continuously throughout a woman's reproductive years, independent of the sleep-wake cycle. However, the hormonal environment that supports this process is influenced by circadian rhythms, with certain phases of follicle development being enhanced during specific times of day. The final maturation of the dominant follicle and the timing of ovulation are particularly sensitive to circadian signals, explaining why disruptions in sleep patterns can sometimes affect menstrual cycle regularity. Melatonin, the hormone of sleep, also plays important roles in reproductive function for both males and females. In addition to its sleep-promoting effects, melatonin acts as a powerful antioxidant that protects reproductive cells from oxidative damage. During the nighttime hours, when melatonin levels are highest, this protection is particularly important for the delicate processes of sperm production and egg development. For both males and females, the reproductive system's response to sleep extends beyond hormone production to include the maintenance and repair of reproductive tissues. Growth hormone, which peaks during deep sleep phases, supports the cellular renewal processes that keep reproductive organs healthy and functional. The increased protein synthesis that occurs during sleep contributes to the maintenance of reproductive structures and the production of the cellular machinery necessary for reproductive function. The relationship between sleep and reproductive health is bidirectional, with reproductive hormones also influencing sleep quality and patterns. Estrogen and progesterone have complex effects on sleep architecture, with estrogen generally promoting lighter sleep and progesterone having mild sedating effects. These hormonal influences help explain why sleep patterns can change throughout the menstrual cycle and during different life stages when reproductive hormone levels fluctuate. Temperature regulation, so important for overall sleep quality, takes on additional significance for reproductive health. The slight drop in core body temperature that occurs during sleep helps maintain the optimal temperature differential for sperm production in males. In females, the temperature changes associated with the menstrual cycle can influence sleep quality, with the progesterone-induced temperature elevation during the luteal phase sometimes affecting sleep comfort and duration. Sleep also influences the production of prolactin, a hormone traditionally associated with lactation but important for reproductive health in both sexes. Prolactin levels rise significantly during sleep, reaching peak concentrations in the early morning hours. This nocturnal prolactin surge appears to support various aspects of reproductive function, including the maintenance of reproductive tissues and the regulation of reproductive hormone sensitivity. As you rest peacefully, your reproductive system continues its ancient work of maintaining the biological foundations of life itself. The hormones produced during these quiet hours, the cellular renewal processes that occur in reproductive tissues, and the intricate coordination between reproductive function and circadian rhythms all contribute to the preservation of one of biology's most remarkable capabilities. Whether actively engaged in reproduction or simply maintaining reproductive health, Your body demonstrates the profound wisdom encoded in its biological systems, systems that connect you to the endless chain of life that stretches back through evolutionary time and forward into an unknowable future. As our journey through the anatomy of rest draws to a close, take a moment to marvel at the extraordinary coordination occurring within you at this very instant. Every cell, every tissue, every organ system we have explored continues its dedicated work, maintaining the delicate balance that allows you to drift peacefully towards sleep. Your bones provide steadfast support while quietly remodeling themselves, your muscles release their hold on the day's tensions, and your nervous system gently dims the lights of consciousness. This is the profound gift of human anatomy, not merely a collection of parts but an integrated masterpiece of biological engineering. Each breath you take engages your respiratory system in its ancient rhythm, each heartbeat circulates life through your cardiovascular network, and each moment of rest allows your body to repair, restore, and prepare for tomorrow's adventures. The systems we have explored tonight will continue their silent vigil as you sleep, ensuring that you wake refreshed and renewed. In the morning, you will rise, not because of any single organ or system, but because of their magnificent collaboration, a testament to the wisdom embedded in every fiber of your being. Rest now, knowing that your body is perfectly equipped for this transition into sleep. Trust in the anatomy that has carried you through this day and will carry you safely through the night. Let the knowledge of your own remarkable construction be a source of comfort as consciousness fades and dreams begin their gentle dance. Sleep well, and let your anatomy carry you home to rest.